title that you can read here. So what would happen if the last caldera-forming eruption in Tenerife were to happen again in the future? So as Juan said, this is part of my PhD that I'm doing at Geosciences Barcelona, and I will explain a little bit more later. But let's start presenting the content of the seminar. I'm going to introduce first what was the problem that we faced at the beginning, and it's actually the reason we started this study. Then we will move to our objective, the main objective of this research. Then I will introduce the geological setting, but also the social, economic, and political context of the area of our case study. Then we will move to the classical methodology section. So how did we do it? Then I will present my main results, and we will discuss them in terms of the policies of disaster risk reduction. And finally, I will show you where you can find this study and the context of my PhD. So first of all, let's introduce the main problem that we face at the beginning and the reason we started this research, and they are the extreme geohazards. So extreme geohazards are low probability but high impact events with a very short unfolding time, but their consequence can last for a very long time. And apart from that, they have the characteristic of producing cascading effects. So cascading effects sometimes are very difficult to predict and to prepare for. So for that reason, they are usually not included in hazard assessment, and they are underestimated in disaster risk reduction policies. So this context, or these two terms, are going to be applied for a specific environment, which are the volcanic islands. Why? Because volcanic islands are environments that sometimes are very vulnerable to different geohazards because of their social, economic, and political context, and also the geographical situation. Let's see a little bit more about these environments, but very briefly. They are, their main monetary income comes from tourism and local activities. So any disruption in these two sectors of the society can have a very severe impact in the future. Then they are usually old colonies. So this is important because sometimes they are very far away from the country that they belong to. So the arrival of the resources or the first aid during an emergency can be a little bit more complex than other continental parts. And apart from that, the population of these islands sometimes is younger than in other continental parts. So they have not as much as, so they don't have a very long history. So they haven't experienced many events or many extreme geohazards during their history since their first settlement compared to other parts. And finally, they have an intrinsic multi-hazard nature because they have grown by both volcanic and other natural processes, but also they have had destruction processes, and they have been modified by both natural and anthropogenic processes. So they are susceptible of natural events such as floodings, landslides, eruptions, earthquakes, but also to human-induced hazards, okay? And in all this context with the volcanic islands and as a specific case, we are going to show you our case study, which is Tenerife. Tenerife is a volcanic island where extreme geohazards have occurred several times in its evolution. Very briefly, Tenerife is the most populated island in the archipelago that it belongs to, which is the Canary Islands archipelago. It receives millions of tourists per year, but no multi-hazard assessment has been done for the island, okay? And why this is important? Because Tenerife has experienced at least twice the sequence I'm going to show you now. So a caldera-forming eruption that gave pyroclastic density currents, high magnitude seismicity due to the collapse of the central part of the volcanic edifice that triggered a mega landslide, and with the impact with the ocean produced a tsunami. So our objective was precisely to do a long-term multi-hazard assessment for Tenerife, taking into account this sequence of cascading effects I have shown you here, taking into account a Labrador eruption, which was the last caldera-forming eruption in Tenerife that happened again around 180,000 years ago, but considering the current topography and demographic distribution to see the impact today or in a near future. So where are we? As you can see here, we are in this red square. From here, we are in front of the southern coast of Morocco in the North Atlantic. And if we zoom in, we will see an archipelago formed by 7 main islands. forming a active volcanic archipelago, and they are La Palma, El Hierro, La Gomera, Tenerife, Gran Canaria, Fuerteventura, and Lanzarote. But we are going to focus on the biggest one, which is Tenerife. Okay, as you can see here, you can see the depression in the central part, which is an overlapping of 3 calderas. Okay. If we move to the geological map, you will see like different grays or gray colors, which consist or correspond to different stages of the evolution of the island. So the darker ones are the oldest part of the island. So Anaga Massif, Teno Massif, and Roque del Conde Massif corresponds to the old basaltic series from the basaltic shield complex, which is the oldest part of the island. And they started to grow up at around 12 to 4 million years ago. Then the island started to grow up along these 2 main rift zones, which is Santiago del Teide rift zone and Dorsal rift zone, and another monogenetic volcanism here. Okay, then we experienced the construction of the Las Cañadas edifice, which is a central volcanic edifice in this lighter color, with the lower group and the upper group. We will see a little bit more later. And finally, we have the construction of Teide Pico Viejo stratovolcanoes in the center of the island. Okay, so if we see the time scale a little bit, very briefly, the original part or the origin of the island I put in light gray because it's not so important for our study, but just to mention them, we have the basaltic shield construction with basaltic volcanism. Then there was a slowdown in this construction, and at around 3.5 million years ago, we have an erosive period. After that, we started to grow up the lower group of the Las Cañadas edifice, this central part that I mentioned before, with phonolithic volcanism together with basaltic episodes. But this is important, this point, because between 2 and 1.5 million years ago, there was a change in the eruptive dynamics, and we started to construct the Las Cañadas edifice upper group. And this upper group is characterized to be a cyclicity, to have a cyclicity. So they are like 3 cycles, 3 phonolithic cycles, starting with the first one that gave the Ucanga formation and ended with a caldera collapse at around 1.07 million years ago. Then the second cycle started with a period of 200,000 years approximately of basaltic volcanism, and then the rest of the cycle was phonolithic, so phonolithic volcanism, and gave the Guajara formation. But the interesting thing here is that it ended again with another caldera collapse and the formation of La Orotava Valley due to a mega landslide, which is in the northern part of the island. Then the first cycle started with, which gave the Diego Hernandez formation, but it started again with a basaltic episode of 200,000 years ago, years approximately again, and ended with another caldera collapse and the formation of the Icod Valley, which is actually another mega landslide produced in the north next to La Orotava. So now the very beginning of this like 4th cycle, let's say, was also basaltic volcanism, but now the last eruptions that we have had in Tenerife are phonolithic. So it seems that we are in the 4th cycle. But the event that we are going to focus on is this from here, which is actually a Labriga eruption that I mentioned before, and is the one we are going to model and simulate to see the impacts if this event were to happen again in the future. How this event occurred, or which were the main events that compound the sequence or the cascading sequence of a Labriga eruption. So let's see with this picture from here, you have the Las Cañadas edifice and the magma chamber. So you had a caldera collapse in the central part with the emission of PDCs, of pyroclastic density currents that covered nearly the whole island with igneous brights, with a layer of around 2 to 20 meters of thickness. It produced high magnitude seismicity with a magnitude between 5 and 7.2 that started to produce some submarine landslides. But then, as the seismic shocks continued, it produced a mega landslide in the subaerial part involving 60 cubic kilometers that when they impact with the ocean, they produced a tsunami wave that left deposits at around 132 meters above the sea level. So all these events are the ones that we are going to simulate with different softwares. So how did we do it? We simulated these 4 main events of the cascading sequence by separately, but sometimes the results from one event were the input parameters for the next event. So we will see it later. So for the PDC, we used Boris 201 software developed by Felpeto et al. 2007 that calculated the maximum cover area by the Ignimbrite. For the seismicity, we use a plugin for QGIS developed by Núñez 2017 that calculated the ground acceleration of the area for a given earthquake. For the landslide, we used a slide from Rock Science 2020 that calculated the factor of safety depending on the PGA that we introduced in the software. So you can see the relationship between these two events in the modeling. And finally, for the tsunami, we used workflow from Kelvin and Dre 2005, and it gave us the propagation of the waves for a given thickness of the landslide. Okay, so you can see how the cascading effects are applied for our simulation. So let's see more in detail how these simulations were done. But first of all, in addition, we have to add the 50-meter resolution digital elevation model as a base for some of these simulations that it was provided by the National Geographical Institute of Spain, and the 50-meter resolution digital bathymetry, which was provided by the Oceanographic Institute of Spain. So for the PDC, we use the energy cone model developed by Sheridan and Malin, which takes into account two different input parameters, which is the collapse equivalent height, which is this height from here, the height at which the eruptive column can collapse and produce the PDC, and the collapse equivalent angle, which is the angle between the line from the collapse equivalent height and the maximum distance at which the Ignimbrite can arrive and the ground. Okay, so we use two different options for this parameter, 2,000 meters and 3,000 meters. They are based on real cases, so real eruptions. And for the collapse equivalent angles, we took a range between 4 degrees and 27 degrees because it was the range recommended by Sheridan and Mellin. And we used each 3 angles. Okay, so for the seismicity, we classified the geological map of Tenerife into 6 groups according to the methodology of Borchardt. I'm not going to explain now in which is the methodology because I will need another presentation, another seminar, but you will have later the information where to find this methodology in the paper, which is this seminar based on. But just to say that with this classification, we obtain the seismic amplification map of Tenerife in terms of the amplification factor of Borchardt for high frequencies. So this map was introduced in the plugin of QGIS, and then we had to determine which would be the epicenter or the type of earthquake. So to do this, we had to choose an epicenter for our earthquake, but the problem is that the epicenter is always located during a caldera collapse in the ring fault that is produced by the collapse of the central part. So as we don't know where is the magma chamber, which is actually the feature that controls where the ring fault is going to occur, so the size of the ring fault is controlled by the size of the magma chamber, and we don't know where is the magma chamber currently, we chose the 2 options, a magma chamber located just under the crater of Teide and a magma chamber displaced to the south with the edge under the crater of Teide. So this gave us 2 epicenters, okay, with this coordinates, and for each epicenter we chose 3 different hypocenters. Apart from that, we tested 3 different moment magnitudes for the earthquake, and we applied 3 attenuation laws because they were the ones recommended by Núñez. For the landslide, we did the slope stabilities analysis in 2 conditions or in 2 situations, which were static analysis without seismic conditions and pseudostatic analysis with seismic conditions, okay? And these 2 analyses were done for 2 geotechnical models, as you can see here. This is the profile of Teide and the Ecot Valley in the north, okay? So here is the ocean. And the unique difference between both of them is that the presence of altered lavas here, and here you can see that there is no altered lava. So just to test the influence of these alteration zones. But the rest areas are, or the rest geotechnical units are the fresh lavas from Teide, the collapsed material of the previous Cañadas collapse or caldera, a water circulation zone, a cohesive volcanic soil, which is called Mortallon in brown. This was the decollement surface of the previous landslide, so we think that it could act again as a decollement surface for the next landslide. And finally, the materials from the basaltic shielding part. And apart from that, we used another, which is called Model 1B. It's the same as Model 1, but instead of considering this whole portion of the island susceptible to slide, we only considered a portion of the island from here, from in front of Las Calvas del Teide to the north, in a situation that we consider this part was already collapsed, so it was not susceptible to a slide. It was not available to slide with the rest of the land. So the weight was not acting in favor of the gravity. And then for each geotechnical unit, just to mention, because we are not going to go in detail with all these values, but we had to give for each geotechnical unit different parameters, geotechnical parameters, and different values for each one. So it was a lot of effort because no data was being collected in this area for geotechnical units, but comparing with other volcanic terrains, there was like a previous processes to do this. But just to mention, then I will explain it later where you can find this information. And then here you can see this is the seismic map. I put in very small, just not to spoil you, because we will see later the results from the seismic simulation. But just to mention that in this case, to use a slide, we need the PGA, so the peak ground acceleration values obtained from the previous simulation, which was the seismicity one, to include them as a horizontal coefficient of acceleration. So we had to change from PGA to this KH by using these formulas. Okay, so for each PGA, you have 3 different coefficients depending on the formula applied. Okay, so the landslide, the factor of safety of the slope was tested for each value that you can see here in this table. So imagine all the combinations that we got. And finally, for the tsunami, we use surface software to draw the landslide area or the possible landslide area, the bathymetry, and we include them in the bulk flow code that was run by MATLAB. And these, again, are the results that you will see later, but they are the results from the slide, from the landslide simulation. But just to put it in small, because I don't want to show you now nothing, just wait for later. And they will all include in the bulk flow code together with other input parameters, just like density of the avalanche block, the yield strength. And for this parameter, we use 2 different options, 50,000 pascals and 100,000 pascals, that they were recommended by Karim Kelfon, and other parameters for the water. Okay, and the thickness that was given by the simulation done by slide. Okay. And what did we get? So 277 eruptive scenarios divided into 14 PDC scenarios, 44 seismic scenarios, 207 landslide scenarios, and 2 tsunami scenarios. So we are going to start with these ones. And these are the type of maps that we obtain. The red area is the maximum cover area that can be affected by the igneous brides from the PDCs. And this option is for a collapse equivalent height of 2,000 meters and a collapse equivalent angle for 4 degrees. So see the difference now from this map to this other. So the only difference, I go back, is to change the degree from 4 degrees to 27 degrees, which was the maximum tested. And as you can see, the only covered area will be the central depression, which is the Las Cañadas caldera, and part of the Icod Valley. If we move to this option, you see the difference, okay? This is just increasing the collapse equivalent angle from 2,000 to 3,000, okay? So you can see with a difference of 1,000 meters of the collapse equivalent angle, we can overpass the Las Cañadas caldera wall and affect nearly the whole Icod Valley, okay? So these are the difference. And finally, you can see the difference in changing from 4 degrees to 7 degrees, that only this part will not be covered by igneous bright. So a change in the degree can also suppose that one of a part of the island cannot be covered by igneous bright. Okay. So for the seismic scenarios, these were the values obtained for the PGA, the big ground acceleration. And as you can see here, they are for the epicenter one, which was the one considering a magma chamber just under the crater of Teide. You can see the difference between the 3 attenuation laws, okay, and the 3 different magnitudes. But these 3 values are the same as these 3 ones and as these 3 ones. So the depth was not influencing the values. So we can remove this variable. But there were very big difference between the magnitudes, of course, but also between the different attenuation laws. And regarding the distribution of the seismicity, we can see that for this epicenter, the main affected part would be the central part of Las Cañadas caldera and the Icod Valley, but also the municipalities located along these rift zones will be severely affected. If we move to, for the same magnitude, we move to another attenuation law, we can see that this distribution is most concentrated around the epicenter. But if we increase, for the same attenuation law, we increase the magnitude, the distribution doesn't change, just change the maximum value, of course. For the landslide and scenarios, these were the results that we obtained. You can see here that we are under seismic conditions. This is for a coefficient, horizontal coefficient of 0.1, which is this one. And you can see here how for the difference analysis methods that we applied, this is also another process that we had to do before because the slide needs to calculate, depending on the analysis that you apply, it calculates with different forces and different it's different methodologies. You can later read more about these methodologies, but just to mention that with a 0.1, we started to have some instability like this, because if it goes below 1, it shows you instability of the slope, and this is the main sliding surface. Okay, and for 0.13, we had instability for all of the applied methods. But if you see this value and you compare with the model 1b, which was the one that we only consider this portion of the island, so as this was already collapsed, this value was much higher. This value is the value where we started to have some instability. So it means that at the very beginning of the collapse of this central part, it's much easier to have the landslide because this KH can be reached more easy than if the collapse is already in their final stages. Okay, so in the final stages of the collapse, it would need a higher KH to produce a landslide. But if we want to know which PGA produced this KH, we have to undo the different formulas that we applied before. I don't know if you remember. And if we want to know which magnitude can produce this PGA, we have also to undo the different attenuation laws. So the results are that we have a larger number of options that can produce the same KH. So it's very difficult to specify a specific magnitude that can produce an instability. This is a difficulty that we face during the research, and it's the only thing we can do now because more research has to be done in the area because we don't have microzonation done in Tenerife and other studies. So this is something important to take into account. And for the tsunami scenarios, you can see here the 2 different scenarios that we tested. These are the results. A first wave of 200 meters approximately that could devastate in less than 10 minutes the northern part of Tenerife and impact with the rest of the islands up to 7 times, like in La Palma, for example. And some of these coasts can act as a new sources for tsunami waves. And in less than 2 hours, we would have the whole archipelago affected. The only difference with this option is that the first wave is a little bit more shorter. It's not 200, it's 180. But the most interesting thing was that there was a delay of 10 seconds of the arrival of the waves to the rest of the islands, but nothing else. And what do our results mean? So the results that I show you are the most catastrophic scenario for Tenerife. And all the rest of the scenarios are possible. They can be possible scenarios, but the one that I want to share with you is this one that I show you here, because it's the scenario or the combination of the scenarios that better coincides with what happened during a big eruption. So if we want to recreate or reconstruct the big eruption conditions, we will have this type of results, which are nearly the whole island covered by ignimbrite. This is achieved with a collapse equivalent height of 3,000 meters and this angle of 7. Las Cañadas caldera and Daycott Valley will be affected by high magnitude seismicity, reaching PGAs of around 0.3, 0.33 Gs. If this PGA is reached, we could have a mega landslide affecting the northern slope of Tavia and Daycott Valley, with a thickness of 500 meters, which is actually the infill of the current Daycott Valley. And if this impacts with the ocean, we will have a 200-meter high first tsunami wave devastating the north of Tenerife in less than 10 minutes. This is achieved for a yield strength of 50,000 pascals. So to take into account, at present, the Tenerife volcanic system is not in a situation similar to that of the last caldera eruption. So reaching the conditions for a caldera-forming eruption may take thousands to hundreds of thousands of years. But the Teide Pico Viejo complex is following a very similar evolution than the previous monolithic cycle, so it is not inconsiderate to consider it might occur again in the future. For that reason, I would like to show you or to share with you this take-home message that what we have been seeing here is an extreme multi-hazard scenario that cannot be managed. It's impossible to manage this type of a scenario because it's extreme geohazard, an extreme event that no resources can be applied to mitigate the risk or the impact. But efforts must be invested in forecasting and prevention well in advance. So this is the most important part, and the first step that we have to do is include this multi-hazard scenario in the PEVOLCA, which is the volcanic emergency plan for Tenerife and for the rest of the Canary Islands. And to finish this seminar, I would like to share with you that this is part of my PhD, which is multi-hazard assessment and risk management in volcanic islands. So we are working in more types of multi-hazard assessment for the Canary Islands and specifically for Tenerife, with other type of events, of course. And where you can find this study. So this study was published in the Journal of Geophysical Research, Solid Earth, with the title of Cascading Effects of Extreme Geohazards on Tenerife, Canary Islands. So here you have the DOI, and you can also scan this QR code, and you can go directly with your phone to the paper. And I would also like to say that I will be in the EGU General Assembly of this year in Vienna in this session from here, Innovative Approaches for Multi-Hazard Risk Assessment and so on. And I will be very happy to be there, meet all of you and answer your questions or discuss any topic. So this is all from my part, and thank you so much. It will be a pleasure for me to answer all your questions. Thank you.